Hello and welcome back to Multivariable Calculus, the video series where we talk about real analysis with a bunch of variables. And in today's part 27, we want to talk about an application of the famous implicit function theorem. Moreover, I also want to state the general version of this theorem and the other one, which was called the inverse function theorem. However, before we start with that, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And also, please don't forget, with the link in the description, you can download additional material like quizzes and PDF versions. These might be really helpful if you want to check out all the details of a given theorem. For example, it's good to have the important inverse function theorem in a written form. The assumptions we need there are just two open sets and a continuously differentiable function f such that at a given point the Jacobian is invertible. And then we can conclude that f is a local C1 diffeomorphism around x0. This is the inverse function theorem in the formulation as we have it already proven, but now we can generalize it to a CK diffeomorphism. Indeed, this is not a big problem because one can easily extend our proof by this fact as well. It's just the statement that the higher order of differentiability of f translates to the local inverse function as well. And please don't forget, k here is always a natural number or the symbol infinity. Indeed, often we have C infinity functions, and now we know that the local inverse is also a C infinity diffeomorphism. Hence, we can easily use this generalized version in the implicit function theorem as well. So in the formulation of the theorem, here we have our function F and it can also be a CK function now. Otherwise, we have exactly the same assumptions as in the last video. So we have a point u0 where the function is exactly 0 and where the partial determinant is invertible. And then we get the existence result for open sets and a function g. This g is the wanted implicit function satisfying our equation for capital F. And now the order for the differentiability also translates to this function g. Simply because in the proof of the implicit function theorem, we use the inverse function theorem. So in particular, if we know that our capital F is a C infinity function, then G is as well. Okay, so these are the general versions of the two theorems as you should remember them. And now we are ready to discuss a nice application of them for C infinity functions. In particular, we will just take a polynomial with a real variable t. This means we have a finite number of coefficients and we can call them a0, a1 and so on. And let's say the last one we have here is an with capital N. So the degree of the polynomial is given by capital N. And of course, a polynomial is always a C infinity function. So let's make a quick sketch of the polynomial and let's consider a 0 of it. So we want to have a point where the graph of the polynomial crosses this t-axis. And this point in t we can simply call t0. And what we actually want to have here is a so-called simple zero. This explicitly means that we have two conditions, namely first p of t0 is equal to 0, but for the second claim we want that the derivative of t0 is not 0. So this guarantees us that the graph here is really crossing the axis. And then we suppose that this 0 is in some sense stable when we change the coefficients a little bit. In fact, this claim is exactly what we want to prove in this video. But before we do that, let's first consider a simple case we already know. Namely, we take a general quadratic polynomial which only has 3 coefficients. More precisely, in order to have a quadratic polynomial here, we have to assume that the last coefficient a2 is not equal to 0. Which implies that finding zeros here is just solving this general quadratic equation. So we have t squared plus a1 divided by a2 times t plus the constant a0 divided by a2 as well. And that's it, and this should be equal to 0. And now by applying your school knowledge, you can write down the general solution formula for this. Indeed, we find two solutions, and let's call them t plus and t minus. And there we have a whole fraction where 2a2 is in the denominator. And in the numerator we have minus a1 plus minus a square root. So in general, we would need complex numbers to see both solutions of this quadratic equation. However, if we assume that we have a simple zero here in the real numbers, then we also see what happens if we change the coefficients a little bit. So if we wiggle the coefficients in a C infinity sense, the zero will also change in a differentiable way. This is simply because the coefficients go into a C infinity function here. However, we cannot say that for a general polynomial because we don't have a formula for the zeros in the general case. But exactly there, the implicit function theorem can definitely help us. We just have to define a suitable function capital F. And as always, we split the domain up into two inputs. And the idea is that we put our variable t here into the second component and all the coefficients in the first component. Therefore, now we call the coefficients x1, x2 and so on. Maybe this is a little bit confusing, but just remember, we want to describe a polynomial where we can vary the coefficients. Therefore, it makes sense to see them as variables now. The only problem we have here is that the naming with the indices is shifted now by 1. Therefore, if we stay with our capital N, the last coefficient here is n plus 1. So in other words, our k here is equal to n plus 1. Okay, but now we see that the whole function capital F is definitely a C infinity function. And moreover, we also have a nice zero for it. Namely, we just have to put in the original coefficients and t0 from before. More precisely, we have to find the point x0, which is given as the coefficient a0, coefficient a1, and so on. So there we have our original polynomial, where t0 should be a simple zero. Hence, simple zero now means something for the partial derivative of f. It's just the partial derivative of capital F with respect to the t variable. And this is just the derivative of the polynomial, and we know this should not be equal to 0 if we put in our simple zero t0. So in other words, this 1 times 1 matrix here is invertible. Hence, all the assumptions from the implicit function theorem are satisfied. So we can just apply it, and we get out that we find a local inverse function called g. And by the generalization from the beginning, we know that we also have a C infinity function here because capital F is a C infinity function. And by the construction of our implicit function theorem, we know this function gets k inputs and 1 output. And this 1 output we can put into capital F again, and then we have this equality for all points in V1. So we see that g of x is the simple zero as a function of the coefficients. And in addition, we also get that this works in a C infinity way. So one conclusion here is definitely that if we would have a general formula like in the quadratic case, then we knew that this formula should be C infinity locally. Therefore, this is the best substitution we have for such a formula because it still tells us how we can calculate with the simple zeros. So for example, small changes in the coefficients will translate into a small change of the simple zero. But please beware, if we don't have a simple zero, this whole procedure does not work. Okay, so this was one nice application of the implicit function theorem, but I can already tell you that we will talk about more later. For example, soon we will talk about so-called Lagrange multipliers, where everything comes together. So I really hope we meet there again, and have a nice day. Bye bye.